Analytical Chemistry 1, Lesson 32. We will look at how you would go about making a buffer solution. The key point is that there should be a substantial amount of both the conjugate acid and the conjugate base, and the ratio of the two should be within a factor of 10. We will first see how to calculate what is needed for a specific buffer. Now, while that implies a process, we will then look at how it would actually be done in practice. We will first develop a nice mathematical tool that will help in analyzing buffers. Make up a solution of acetic acid so that it would be formally 1.00 millimolar, but also add some sodium acetate. Now, this is a salt of acetic acid that completely dissolves in water to give the acetate ion, which is the base conjugate to acetic acid. Let's specify that you add enough sodium acetate so that the solution would formally be 1.50 millimolar in acetate. Now, it's not too difficult to write out the various equations. There are two mass balance equations this time, and you can solve them and use Goldseek and Excel to determine the pH. But an interesting thing happens. If we were to put just acetic acid in solution, it would, of course, partially dissociate. On the other hand, if we were to put just acetate ion in solution, it would, of course, partially associate. And this is just what the reaction equation is telling us. If you add some acetate to the acetic acid solution, Le Chatelier's principle tells us that it will tend to drive the reaction backwards so that there is less acid dissociation. The converse is true if we started with an acetate. Adding acid will drive it to products so that there is less association. The end result is that if we mix together both acid and acetate, they will tend to prevent either from reacting to form the other. The assumption that we make, and it is a pretty good one, is that the formal concentration of acid is also its actual acid species concentration, while at the same time the formal acetate concentration is the actual acetate species concentration. Recall the form in which we rewrote the acid dissociation constant to solve for H+. We can substitute these values into the rewritten Ka expression to solve for the hydronium ion concentration. We obtain H+ equals 1.17 times 10 to the minus 5 molar. This gives a pH of 4.933. This is in the range covered by the low acetic acid concentration solution mentioned before, except this time there is a large amount of both acid and acetate. This will make a very good buffer. Take a look at the equation we used. Since we are generally after pH, we can rewrite this as follows. Take the negative log of both sides and separate the terms to give this new expression. This is called the Henderson-Hasselbalch Equation. Now note that it is just the acid dissociation expression. It's not something new, but it is presented differently. Now the equation is exact, except for activity, of course. This is not an approximation. But the approximation that we do use is to insert the formal concentration for the species concentration for both the acid and its conjugate base. If the acid and base formal concentrations are the same, the log term is 0, and pH equals pKa. A larger value for acid and the pH decreases, a larger value for the base and the pH increases. We generally consider a buffer to be effective if the ratio lies between 10 and 0.1. That means that we can successfully use acetic acid as a buffer system for desired pH values that lie between plus or minus 1 pH unit of the pKa value. By using different chemical systems, we can find a buffer system that can cover all required pH ranges. A couple of examples. 0.015 molar in acetic acid and 0.006 molar in acetate. Plug it into the Henderson-Hasselbalch equation to get a pH of 4.358. There is more added acid, so we would expect a more acidic pH than the pKa. A different example. 4-nitrophenol has a pKa of 7.149. Make a buffer with 0.1 molar 4-nitrophenol and 0.3 molar of the sodium salt. Use Henderson-Hasselbalch to get a pH of 7.626. So the Henderson-Hasselbalch equation is the tool that will let us determine the parameters of a desired buffer. So what do we do when we need to create a particular buffer? The first thing we need is to decide on the value of the pH at which we want the buffer to be fixed. Let's say we want to buffer our solution at pH equals 6.80. The next thing we need is to identify the acid-base system we will use. Recall that a buffer is effective in a range plus or minus 1 pH around the pKa of the buffer system. On page 209 of your textbook, Table 2.9 lists almost 50 buffer systems to choose from. They have pKa values that range from 1.59 to 12.74. You can find a system that will suit your needs. If we look through this table for a system with a pKa in our desired range, We find 14 viable options. Now, in practice, there will undoubtedly be other considerations that will help you make your choice, but for right now, let's assume we'll use the imidazole-imidazolium hydrochloride system with the pKa equal to 6.99. We turn to the Henderson-Hasselbalch equation with this information. We can solve for the ratio between the two forms, but we need additional information before we can pick specific values for each species concentration. We might, for instance, claim that the formal concentration of the buffer components is to be 0.01 molar. So the sum of the acid and base forms concentrations is to be 0.01 molar. By reorganizing the equations, we can determine that the acid concentration is to be 6.047 millimolar and the base concentration is 3.92 millimolar. You can plug this back into the Henderson-Hasselbalch equation to confirm that it will indeed provide a pH of 6.8. The approximation we invoke at this point is that we can determine how much of the imidazole to add and how much of the imidazolium hydrochloride to add and assume that their formal concentrations will be these particular species concentrations. This is what you will be assuming in this class. Both of these substances are solids, so we can weigh each out and create the buffer. Now, this works well for questions on an exam, but in real life, it would not happen this way. How would you actually make such a buffer? Well, the Henderson-Hasselbalch equation is just a rewriting of the equilibrium constant. The way we use it is to ignore activity coefficients. In real life, the chemical systems do not ignore them. Also, our water may have picked up some dissolved CO2 from the air, and it's slightly acidic from that, and other impurities, and who knows? So how can we deal with this? Well, it's quite simple in practice. Prepare a solution, now the volume depends upon your needs, of imidazole such that it has a formal concentration of 0.01 molar. Insert a pH meter into the solution. It will be reading a basic value. Add a strong HCl solution until the meter reads 6.80. The added acid converts imidazole to the imidazolium ion, and when their activity is such that the pH equals 6.80, you stop adding acid. Simple, right? So when is a buffer most effective? There is a property called buffer capacity. It is defined by these derivatives. They are asking how much strong acid or strong base is needed to induce a change in the system's pH. The sign difference is because adding acid lowers the pH and adding base increases it. If we were to determine the derivative, the buffer capacity, as a function of pH, we would find a curve such as this. Now, the peak of the curve is when pH equals pKa. This is the point where the system requires the most amount of added acid or base to effectuate a change in pH. Put another way, this is when the system is most resistant to pH changes. This is when a buffer is most effective. There's another interesting point to be made. If we continue this graph to very high or very low pH, the buffer capacity also increases. At high pH, the water hydroxide system is buffering the solution. At low pH, it is the hydronium water solution that is buffering the solution. Looked at another way, when the solution is already a very strong acid or a very strong base, adding more strong acid or base does not change the pH very much. For most practical purposes, we can buffer solutions with the pH between about 2 and 12. Now, just to summarize our introduction to buffers. A buffer is a solution that contains a substantial amount of weak acid and its conjugate base. The buffer is most effective when its pKa is close to the desired pH of the solution. A buffer performs well within plus or minus 1 pH unit of its pKa. It does an okay job at plus or minus 2 pH units. The reason it resists the pH change is that added acid or base reacts with the buffer base or acid, so that pH remains under the control of the buffer system and not that of the added acid or base. However, if a lot of acid is added, a lot being determined by the formal concentration of the weak acid-base system, then the buffer can eventually be overwhelmed and the pH begins to change substantially. Buffers, like an acid base, depend upon activity coefficients and upon temperature. We use the Henderson-Hasselbalch equation. The equation is exact if we had activity coefficients, but we use the approximation that formal acid and base concentration equals the species concentration. And this can fail if the acid-base system is very strong, pKa down around 2 or 3, or if the solution is too dilute. A more complete analysis following this systematic approach to equilibrium would be needed to accurately calculate the pH. Otherwise, We can use this phrase to describe making up a buffer. What you mix is what you get.